Okay, so let us first solve for our previous quiz on Theory 1, quiz number 2. So for the problem on the dead load, we have, may I read the problem? Mr. Marvin Lopez second floor building is being utilized as office area for an engineering consultancy firm. So the floor slab is a concrete reinforced stone 100 millimeter thick, also carrying suspended metal lat and gypsum plaster. So number 1, we should consider here the floor slab is made of concrete reinforced stone that is 100 millimeter thick. At the same time, it carries here a suspended metal lat and gypsum plaster. So for the dead load, it consists of concrete and dead load of the ceiling. So we refer to the table containing the unit weight for the dead load of concrete. So we'll just refer to the table 1-2, and we can see here on the table 1-2 in SI unit we have 23.6 for that one. Okay, and then for our ceiling, we can see here that suspended metal lat and gypsum plaster has a pressure value equivalent to 0.48 kilonewton per square meter. So that we're gonna utilize those values. So this is simply just equal to gamma times the volume. So 23.6 is multiplied by the tributary area, that is 4/5, and by the thickness, so that we will be having here a 47.2 kilonewton. For the dead load in the ceiling, we have 0.48 as a pressure. So we'll just have to multiply that by the area. Okay, so we have 9.6 kilonewton. So adding that one, we have 56.8 kilonewton. That is our answer. Okay, for letter B, what is the resultant of the live load if its panel is 4 meters by 5 meters? So we'll refer to the table of the live load under office building or office floor building. So let me refer you to the table. So the table for an office facility for SI unit, again we have 2.4 for that. So that will be our reference. 2.4 by the area is 48 kilonewton. So that will be our answer for letter B question. So may we now proceed to problem number 2. So for number 2, 10 square meter tributary area is being carried by 0.25 by 0.4 meter concrete reinforced stone with a length of 4.5. The beam carries a floor slab 125 millimeter thick and a wall of 2.7 meters high. This wall is made up of exterior stud with brick veneer. So again, for letter A, we'll just have to take note of the permanent items that are mentioned in the problem. So first we have a slab. Again, this is gamma times the volume. So we have gamma of 23.6 for reinforced concrete stone or concrete reinforced stone. This is the area, this is the thickness. So we'll have 29.5 kilonewton for that. And then for the beam itself, again, it is also 23.6 times the volume of the concrete. This is the cross-sectional area, 0.25 by 0.4 rectangular area times the length of 4.5. So that will be having a 10.62 kilonewton for that beam. okay, for the self-weight of beam. So the total is 40.12 kilonewton. So for letter A, it is only concerned with the self-weight of the beam and the slab. So for letter B, we'll just have to add the dead load of the wall. And for a wall made up of exterior stud with brick veneer, again we will refer to the table of the dead load. We can see here exterior stud walls with brick veneer equivalent to 2.3 kilonewton per square meter. So we're gonna use that, multiply it by the height. So remember, this is kilonewton per square meter times height of meter. We'll have kilonewton per meter as a unit. So 6.21 here will be added to 8.92. That will be the total distributed dead load including the wall, equivalent to 15.13 kilonewton per meter. And that is the answer for number 2, 2B. So moving on, for number 3, we have here a reinforced concrete. So it refers to stone, reinforced concrete stone. We have here a beam of composite shapes. So of course we would like to have a composite area to divide these areas, okay, in computing for the concrete area less the area occupied by the 16 millimeter diameter bars. So of course this is divided by, let us assume here a rectangle, two triangles, rectangle and two triangles. Okay, so this is gamma and this is the volume. Okay, so first we have 1.2 by 0.2. So this is the area, 1.2 by 0.2, this one. And then 0.15 by 0.2, where's that? 0.15 by 0.2. It is actually the two triangles here. Because this triangle here, we have a dimension, this is 0.15 and this is 0.2. So this is times 2 over 2 because we have two triangles. So 1/2 base times height times 2. 1/2 times 2 will just be equal to 1. That is why we have 0.15 by 0.2 here. And then finally we have this one, okay, here, 0.7 by 0.15. Okay, so those are the areas for the concrete, and then we're gonna subtract here the 7 areas of 16 millimeter diameter. Okay, so by that, multiplying it by the gamma times the volume, we'll be having 8.82. So I should say this is an area, okay, the cross-sectional area minus the cross-sectional area of the rods, or 7 pieces. Okay, so we have here 8.82 kilonewton per meter. And then for the steel dead load, we have 77.3. This is the gamma referring to the table. So here is the table, steel cold drone, that is equivalent to 77.3. So going back to our solution, we have 77.3 times the 7 areas of 16 millimeter diameter. Okay, so we have 0.1091 kilonewton per meter. So for the dead load, okay, we'll just have to add this one. So this should be at 8.82 plus 0.109. So we should have here 8.92. So 8.82 plus 0.109, that is 8.92 kilonewton per meter. Okay, moving on. We have here a cross section of a flooring. So as we can see here, this has a layer. And the top layer is 75 millimeter thick cinder fill, and this is 100 millimeter thick reinforced concrete stone resting, or okay, so it is carrying a metal lath and gypsum plaster underneath. So again, we will note on the permanent items on these structural elements. First, we have the dead load for the floor fill. So it is 0.017 times the thickness. We have 1.28 kilonewton per meter squared. And for the dead load for the slab, we have 23.6. See, this is the gamma times 0.1, that will be 2.36, yielding to a unit of kilonewton per square meter. For the dead load of the metal lat, that is 0.48 kilonewton per square meter. So directly we're going to add those ones and come up with this 4.12 kilonewton per meter. So floor fill here came from the table of the dead load. So where's that metal lat? We have here 0.48 for that. And then for the floor fill per millimeter, that is 0.017. Okay. So here it is, 0.017 and 0.48 kilonewton per square meter. So moving on to the next problem, number 5. So this time we are concerned with the live load for a 4-meter beam carrying a floor occupied as chatter with fixed seats. Assume a tributary area of 8 square meters. So number 1, we are going to determine what is the value of the live load when it is being used as a chatter with fixed seats. So we refer to the, so we can see here that the live load for a chatter with fixed seats, we have 2.87 for SI and 60 PSF for English. So we use 2.87 as we are in SI units. So 2.87 times 8. 8 here is area. So the unit square meter will yield 2 kilonewton per meter. Okay. And then divide it by 4. By the way, 2.87 kilonewton per square meter times 8 square meter will yield 2 kilonewton. Just divide that by the length of the beam to come up with a distributed load of 5.74 kilonewton per meter. Okay, so that is for number 5. So moving on to the number 6. So number 6 is an example of live load reduction. So it mentioned that the building is a 3-story, or it is carrying more than 1 story. So it is being used as a school building, and the columns are spaced at 4.5 meters on both directions. So the roof deck is determined to have a live load occupancy of 1.9. So if we have a roof deck with a regular occupancy, we do not need to reduce that one. So it will remain to be 1.9. So what we are computing here now is the floor load from second floor to third floor. Okay, second floor and third floor actually. So we use this formula, L is equal to LO times 0.25 plus 4.57 all over square root of the influence area. So the influence area is the live load element factor times the tributary area. So as we all know that the live load element factor is equal to 4 for an interior column. Okay, for an interior column, that is equivalent to 4. And then 4.5 by 4.5 is the adjacent tributary area that the column carries. So it is just actually a rectangular one. So it will yield to a value of 81 square meter, that is greater than to the requirement, or to the minimum requirement of 37.2 square meter. So meaning our basis is 37.2 square meter area, the least area, so that we can implement our live load reduction. So that is a check mark here. Okay, so proceeding to the reduction itself, substitute the values, then we will yield to live load or reduced live load of 4.47 kilonewton per square meter. This is for just a single live load for a single floor. Okay, so what we do for letter A, determine the total live load carried by the column at the ground floor level. We'll just have to multiply it by 2 and then add the roof load. Okay, so when we say at ground floor level, ground floor carries the second floor, the suspended second floor, and the suspended third floor plus the roof live load. That is why this is multiplied by 2. And then we will yield to 4.8 kilonewton per square meter. So this is the pressure on the flooring. And if we are concerned for the live load per column, we'll just have to multiply it by the tributary area. That is 4.5 by 4.5. And then we'll come up with 97.2 kilonewton for that. And then for letter B, we'll just have to deduct one floor because we are now in the second floor. And the second floor level carries only the third floor live load as well as the roof live load of 1.9. So adding that one, we have 3.35. And then for the live load column, we just multiply it by the tributary area, 4.5 by 4.5. Finally, we have 67.84 kilonewton for a live load carried by the column at the second floor level. Okay. So next we have number 7. For number 7, what will be the reduced live load for an interior column having spacing on adjacent spans of 37.5 feet? The column carries one floor of private hotel rooms as building occupancy. So for our influence area, having a live load element factor of 4, multiplying it by the influence or the tributary area, 37.5 by 37.5, we come up with this much greater than 400 square foot. So, and that is okay because we exceeded the minimum requirement. Okay. So we employ the formula in terms of English unit. So we will be having a value of 18 PSF. So 18 PSF is less than 50% of 40 because the original loading is 40, okay, for a private hotel room. So having said that, 18 is reduced too much. When we say too much, the requirement or the minimum reduction would only be equal to 50% of the original or the unreduced live load LO, and that value is 40. 50% of 40 is 20, so we should not reduce that beyond 20. So when that happens, therefore we'll just adopt our limit for that, and that is 20 PSF. Okay, so I would like to reiterate that we will not maintain an reduced live load of 40, but rather we'll just have to adopt the 50% LO, which is 20 PSF. Okay, next. So for number 8, we have here a framing system. We are required to determine the influence area of the column at grid C3. So this is C and this is 3. So we're referring to the edge column here below. So referring to the table of KLL, we should use 2 for this edge column carrying a cantilever beam. Okay. So the tributary area for this one is the half of this. Okay, we have that one. What is the tributary area? So first we wanted to half this one, okay, and then half this one, and have a projection here. So this will be the tributary area, and this is 2.5. Half of 4 is 2. What remains here is 1 meter, okay, and this is also 2. That is why if we're going to have the tributary area, we have 2.5 by 2 for this one and 1 by 2 for this one. That will yield to 7 square meter. Okay, and then multiplying 7 by 2 meters, or sorry, live load element factor of 2, this should be 2. So 7 by 2 is 14 square meter. Okay, next. For the 9th problem, what is the reduced live load for an interior column space at 12 feet directed perpendicular at both directions for a light storage warehouse? So referring to the table, the original or unreduced live load is equivalent to 125 PSF. So we have here a notation that we are going to maintain this since we are not allowed to reduce a certain loading that exceeds 100 PSF for English units. And for SI unit, we have a limit of 4.79 kilonewton per square meter. Okay, so again, LO is maintained 125 PSF. So this is the answer for number 9. So number 10, what is the live load for an occupancy of heavy storage warehouse? So although they have given element factors here as well as tributary area, we are not allowed to reduce a certain unreduced live load equivalent or exceeding 4.79 kilopascal. That is why we're going to maintain 11.97 kilopascal for this. Okay, next. So we now proceed to the wind load problem here. So 10 meters here facing the front with this ridge here. 10 meters here is considered as L, and then perpendicular to that is, this is B. Okay, this is L. Okay, should be L. This should be L, and that should be B. Okay, so this is L and this is B. Okay, so now before we are going to substitute in the formula of QH, or this is QZ actually, for English units shall be equal to 0.613 kz, kzt, kd, and v squared. So practically, we convert first our v equivalent to 250 kilometers per hour to meter per second. We have here a conversion factor 1000 meters equivalent to 1 kilometers, and an hour is equal to 3600. Multiplying that and dividing that by 3600, we have 69.44 for that v. And then for mean height, we need also to compute for the mean height. Okay, it is the half. It is measured from the half of this one, half of that. Okay, up to this one, this point. So that is the needed mean height, or 6 plus the half of this. So we can determine this dimension. This is 5 tangent of 35 degrees using the tangent function. So therefore 6 plus 5 tangent 35 degrees for the mean height, and that would yield to how many? 7.75. So it will yield to 7.75 for that one. Okay, so now that we have known this v and 7.75, we move on to the windward pressure. So remember that the windward pressure is to be used by QZ, that is shown in the table. It should be used with QZ. Therefore, referring to the windward, we should consider the different heights. Okay, so we have 7.75. Perhaps we can consider this 3 height plus 7.75 as our QH, because this is 7.75 is the highest, or the mean height already. So anything within this range that is below this value, we'll consider that as our Z. So number one, we should have Z and value of Kz as well as Qz for this height 4.6, 6.1, 7.6, and 7.75. So again, we use this one Qz, substituting the values of Kzt and Kd as well as V squared. Kz here is left because we have to consider different values for Kz and Qz at different height. However, we do not know yet what is the Kz for a certain height of 7.75. So that could be obtained by interpolation. So from the table, of course, from this table, we should get the values of Kz. So on height, at the height of 7.6, this is Z, we have Qz, sorry, this is Kz, rather, this is Kz. If we have 7.6, there will be a corresponding 0.94 value of Kz. And if 7.75, we do not know this, right? This is unknown. And then we go to the next 9.1 and 0.98. That is why we can find these values. This is Z, and this is the corresponding, sorry, Kz. So by that we can interpolate, just pair the lower limit to the unknown identity, and then the upper limit to the lower limit, same through this with this Kz side. So on that premises, we have 7.75 minus 6 all over Kz minus 0.94, then 9.1 minus 0.76, and then 0.98 minus 0.94. Just follow the bracket there. Okay, we have here 7.75 minus 7.6, here it is. And then the other side, Kz minus 0.94, this one. And then similarly, we'll just do it, the upper limits, okay? So by manipulation, we have Kz 0.944 for a mean height of 7.75. So we're now tabulating here the corresponding values for Kz and Qz at different height levels. Okay? For the highest, as we have been saying, that will be considered as, sorry, this should be QH, okay, or the Q at the mean level. Okay, so therefore, what is the value of QZ? We adopt this 2790.66, or this should be indicated as QH. So this is the answer for this question. And then for the pressure will now go back to the formula. P is equal to Q GCP minus Q GCP I believe this is QH, and this shall be QZ, okay, for the windward wall. So for the pressure at the windward wall, Cp from table, we use L over B for all values is 0.8. So if we check that one, okay, let us check that one. So here, windward wall for all values is 0.8. And again, this is to be used with QZ. Okay. Now, we use Cp is equal to 0.8 for all values. So therefore, there will be different levels as tabulated above. First, we have at the level of 4.6. So at the level of 4.6, we'll just have to determine the corresponding values here. The QZ for 4.6 is 2,512, and then these are similar values that will be used all throughout on this level. Okay, so we'll have a steady value of 502.32 plus or minus, because plus or minus 0.18, and then this is 1,708.69. So for the lower limit, what is the lower limit? This one, 1,206.37 for the lower limit at a level 4.6 at the windward wall. Okay, so for the its at upper limit, it is 2,211.01 when we are going to use plus sign here. Okay, so we're going to do that at the next height level of 7.6. The same formula, we have QZGCP minus QGCPI. The QZ for 7.6 Z is 2,778.84, multiplied by the gas effect factor for a rigid structure, 0.85, and then 0.8 for its Cp for all values of windward wall. Then this is a steady value again. We're gonna add that one. We have the upper limit. If we have a difference, we have this lower limit. So for the question of lower limit, we have 1,387.29 Pascal. For the upper limit, we have 2,391.93 Pascal. And then finally, at Z at equal to 7.75 meters, this time we'll use here QH. Okay, so QH, this is also the same. When we have a lower limit, we have to deduct that one. We have 1,395.33 Pascal, and the value for the upper limit of the pressure on the windward wall at the height of 7.75 is 2,399.97 Pascals. Okay, and now for the leeward wall, sorry for that. Okay, for leeward wall, this time we need to use L over B, and L over B is 10 all over 7. 10 over 7 will be equal to 1.43. So if we go back to the table, Okay, stable. We are in the leeward wall already. We have 1.43, so you cannot find 1.43 between these ranges. Okay, again, we are going to use interpolation in order to come up with the values within negative 0.5 and negative 0.3. So we're going to use value of L over B, 1 with corresponding CP of negative 0.5. So somewhere here is 1.43 for L over B. So we're gonna use the upper limit to negative 0.3. Okay. So we note here that this is to be used with QH. Okay. Okay, so here it is. We interpolate by using those values, the upper limit to the lower limit, the mid unknown to the lower limit, and also for the other side. By the way, this is the L over B, and this is the corresponding pressure coefficient. Okay, so we come up with Cp is equal to 0.414 for an L over B of 1.43. So basically, what is the value for Cp at leeward wall? So we got that by interpolation by negative 0.414. So we just substitute that. Okay. So again, this is to be used with QH. Okay. So if this is QH, we do not need to have height of different levels. So we'll just use the mean height for QH. Okay. 2790 to 790. So this is remain to 502. We have negative 982.03. If we have a lower limit, we have negative 479.71. That is a suction pressure. For the upper limit, for the windward, sorry, this is leeward wall. Leeward wall. Okay. We have negative 1484.35. Okay. Finally, we proceed now to the roof. Of course, wanted to have a 35 degrees angle for that with an H all over L of greater than 1.0. Where did we get H over L? Okay. So H over L, we arrive at Cp is equal to negative 0.2. So where did we get that? H over L. So a while ago, H is 7.75 with an L of, what is L? L is equal to, where's L here? 10. Okay, L is 10. And that is 10. H over L is 0.78. So where's that in the table? 0.78. At 35 degrees, we have here in between this one, okay? But here we just adapted a value nearest to that is negative 0.2. But basically we should have to interpolate. However, as we can see here, that is already negative 0.2, 4.5, and 0.2 for a value that is greater than or equal to 1. So we're just working for negative 0.2 and negative 0.2 for a value of 0.5 h over L and a value greater than or equal to 1.0. So we're just working with that one. Therefore, we'll just adopt a coefficient factor equivalent to negative 0.2, and that will be directly substituted on the formula. So this remains to be negative 502.32 here, or plus or minus 502.32. So this is a suction pressure, negative 976.33. So finally, we have a lower limit of negative 474.41 for the value of the lower limit at the windward at the roof. Okay, and then the upper limit of the windward at the roof is negative 1479.08 Newton per square meter. Okay, so this is the solutions for your previous quiz for your reference. Thank you.